Okay, we had just gotten the rest of the ds part, and so let me go back to where I was setting this up. I had the limits, I had the dy d theta put in, and the rest of the ds is just dy d theta times ry cross r theta. And I'm going to put that in comma notation to make it a little bit more convenient, but I am going to put it in terms of r theta. Now, how did that get to be an r? Ah, yeah. Sorry about that. The r crept in there because it was in a hurry. R here is 1. Okay. There's no radius. There's no variable radius. The r here is 1. I was thinking of a version of the problem where this would be r squared, and you'd have an r everywhere. So you might have been wondering, what the heck is r here? It's not a variable in particular. That would be 3 parameters, r, theta, y. That would be full cylindrical coordinates. That's probably the other reason I was putting the r in there. This is an actual cylinder of fixed radius 1. And so remember, it's very easy to get confused with parametrizing a specific cylinder of a fixed radius and using the full power of 3D cylindrical coordinates, where this is a variable r. Here, that's just a constant, and it also happens to be 1. And so everywhere I had an r. Thank goodness, it's really not that hard to fix. I just put this in everywhere. I just take it out everywhere, rather. Okay, so the r is going out. So there's my ds, fully parameterized. And now I'm almost done with the setup, because now finally the f comes in. Oh, I'm almost done with setup for S1. And then there's S2. These problems can get a little long. And so that is xi plus yj plus 5k, and x and y are cosine theta and y, respectively. So that's cosine theta, comma y, comma 5. Whew! Okay. And let me just finish the setup, but I think I'm going to, I don't know if I want you guys to sit through me just grunging through the integral, because the setup is the hard part. When I do this dot product, I get cosine squared theta. The y happens to not match with anything, and then plus 5 sine theta dy d theta. So that's the integral over S1. That's the flux over S1, that cylindrical piece. Okay. Now what about S2? Well, that's a plane, but it's also really important that it's a plane that if you project it over to here, it becomes a circle. So we really want to use polar in x and z, just like we were doing for that cone example, the other one I did. So we're going to use polar in x and z, and then let just y come out of the fact that it's 2 minus x. Okay, so we're going to use parameters. Now r really is going to come into it, r and theta. X is going to be r cos theta. Now it really is there. I'm really sure this time. Z is r sine theta. And y is equal to 2 minus r cosine theta, because it's 2 minus x. Here it was the upper limit was 2 minus cosine theta with a 1, because that was just where this boundary hit this cylindrical boundary hits the edge of that elliptical region. Here, I need the whole elliptical region itself, from r equals 0 on the y-axis out to r equals 1. Okay, so the limits for that are going to be 0 to 2 pi again, but now 0 to 1, because I'm really talking about taking a point and using its shadow on the xz plane to describe that point, and that's a unit circle in the xz plane. And we're going to get a dr d theta, and we can put in the f already, I guess. Now, in terms of that parameterization, that's r cos theta, comma 2 minus r cos theta, and then 5, dotted with, and then that's where we have to put in the partial derivatives. So let's do that. R dx dr dy dr dz dr. You can see how we'd really like to get quick ways of doing these calculations. They are significant to get anything out of a significant example. dy dr is minus cos theta, and then sine theta. I didn't pick the simplest one, and I think the ones I tried to pick the ones in your homework to be a bit simpler. R theta dx d theta dy d theta dz d theta, and that's going to be minus r sine theta. Oops, no parenthesis. Plus r sine theta, r cos theta. And the cross product. And one thing we know about the cross product is we know what direction it should come out in. It should be orthogonal to that plane. So the direction should be constant. That's always a good check when you're parametrizing a plane. And again, we need the magnitude information as well. But that should be fairly simple, because the magnitude information just has to do with the density of the grid lines and how big or small the grid squares or parallelograms are. And this is polar. We kind of know the pattern there. So we expect to get an r out of it, and we're kind of hoping that all of these sines and cosines are going to go away in some simple way. So we're going to get minus r cosine squared minus r sine squared. Aha, that's minus r. J with a secret minus sign. Then r cosine squared plus r sine squared. So minus ri minus rj. And then r sine cosine minus 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 r sine cosine, and that's a 0k. And that's right, because even though it's not super obvious from the picture, this plane that's cutting this, I didn't do a very good job, but the plane that's cutting this, remember, is a vertical plane. This didn't involve z. No z. And so the normal vector is just 1, 1, 0. And we're getting exactly minus r times 1, 1, 0. Aha. So now that's going in the wrong direction. So we just flip the order, and that's going to be ri plus rj. And that's exactly what we should expect. What we're getting here is something that's in the right direction, I plus j. That would be the outward normal with length √2. And we're just multiplying that by r, because if you look at the grid lines that you're going to get, it's like this pattern of ellipses. Those are packed tightly in here and bigger outside, and that's exactly that r Jacobian factor that we've been familiar with in one form or another since we started using polar coordinates. Okay, so now I'll go back to here. I've got the dot product there. It's ri. It's just r0. Really rather simple. And if you do this a lot, and it's maybe guessable, but we really needed to go through it to be careful. Okay, so let me skip that over to the next page. 0 to 2 pi, 0 to 1, r squared cosine theta. That's the dot product of the x ones. And then plus 2r minus r squared cosine theta. Hey, wait a minute. That's interesting, because these were equal, and these had a very similar nature to them. I'm getting a lot of cancellations, so that's really nice. And then plus 0. So I actually get something very simple. I get the integral over the unit circle of 2 RD theta. That's 2 times the area of, the unit disk, I should have said. So that part is actually easy. It's 2 pi. If you don't see that as that kind of area trick, you can just integrate it out. This guy is not as simple, I don't think. I didn't look at the actual final answer for this, but this part is really something you have to calculate out. This part actually turned out to be fairly nice as a 2 pi. Okay, so to finish off the problem, you'd do this integral, you'd add the 0 contribution from the left-hand side, and the 2 pi from the right-hand side, and the more complicated thing from the boundary. And there might be some nice cancellation I didn't check in advance, to see about this one. But we're going to be able to do this in a much easier way with the divergence theorem.